Okay, geometry students, here we go into section 6.6. So far in this chapter, we've spent a lot of time talking about some of the main families of quadrilaterals out there. We've talked about parallelograms extensively, and then in 6.4, we introduced three new specific types of parallelograms, which were rhombuses, rectangles, and squares. Now in 6.6, we shift gears a little bit, and it's important to note that unlike those three things that we talked about in section 6.4, when we go to define these two terms today, trapezoids and kites, and we're starting, as you can see here, with trapezoids, this definition does not begin by saying that a trapezoid is a parallelogram. That's the way the definition for both rectangle and rhombus and square, actually all three of them, began. This one doesn't. So it's important to note that a trapezoid is a quadrilateral, which is a generic word for a four-sided polygon that has exactly one pair of parallel sides. Not more, not less, exactly one pair. So what I have drawn for you underneath right here, quadrilateral T, R, A, P, get it? Trap for trapezoid there. That is an example of a trapezoid, everybody. Why? Let's look at the definition. This is a quadrilateral. It is clearly a four-sided polygon, and it has exactly one pair of parallel sides. Line segment TR up here on the top is parallel to line segment PA down here on the bottom. But what's important to note is that line segment TP over here on the left and line segment RA over here on the right are pretty clearly not parallel to one another. If those two segments were parallel, we would have a quadrilateral with two pairs of parallel sides. That would be a parallelogram. So, it is very important to understand, everybody, that a trapezoid is not a parallelogram, and a parallelogram is not a trapezoid. If we were doing Venn diagrams, these two would be mutually exclusive. This would be trapezoids over here, this would be parallelograms over here, and there's no overlap at all between the two. It's not like we can slide this, oh, that didn't work. It's not like we can slide one over and get a typical Venn diagram, which looks something like this, where there's some type of overlap. That is not what is happening in this case. So, a trapezoid is something totally different from a parallelogram, a quadrilateral with exactly one pair of parallel sides. And a little bit of vocab, everybody, as we are moving through here a trapezoid. So, three things that I wanted to point out right here. The two sides which are parallel to each other, in this case TR and PA, are called the bases of your trapezoids. Now, I want to take just a moment and talk about that word right there because it's misunderstood and that can be a little bit dangerous, not just for what we're doing right here today with trapezoids, but especially what we're going to be doing in about a month's time, everybody, as we move into chapters 11 and 12 in this geometry book. When we start talking about area and volume of solids, I take that back, it was chapters 10 and 11. When we start talking about area and volume, some people, are going to have a really hard time because they hear the word base and they think of basement or the base of a statue or the base of a building. They think that a base has to be on the bottom. Now, the way I've drawn this trapezoid, PA is one of the bases and it is on the bottom. All right, but of course you have to realize then that according to the definition we just wrote down, you also have another base up here on the top. But what can get dangerous, guys, is if I draw you a trapezoid, and there's no reason I couldn't, that looks like this, and told you that this left side is parallel to the right side. Now, because people usually think incorrectly base has to be on the bottom, they'll tell me that this side right here is one of the bases. And that is incorrect. Base does not mean bottom. Base in a trapezoid means the parallel sides. So in this case, you've got one base here on the right and one base here on the left. All right, so base doesn't necessarily mean bottom. Second term that I want to define here within a trapezoid are the legs of a trapezoid. And in this diagram, it's line segment TP, which was the one I was pointing out here on the left, and RA, the one over here on the right. Those non-parallel sides, those are the legs of your trapezoid. So back to the drawing that I made over here in red on the right, this trapezoid is actually kind of standing up on one of its legs, and here's the other leg there as well. So again, everybody, base doesn't mean bottom. The bases of a trapezoid are the parallel sides, and the legs are the non-parallel sides. And you'll always be able to tell the difference between those, because if you had two pairs of parallel sides, you would have a parallelogram and not a trapezoid. And then the last vocab bit right here that I want to talk about are what we call pairs of base angles. And a pair of base angles, for example, angle P and angle A. Now that would be this angle right here and this angle right over here. Now you'll notice, guys, I put a different number of tick marks right there. It certainly doesn't look to me like those angles are congruent. But P and A together make up one pair of base angles because they both touch the same base. Listen to this, both angle P and angle A touch base PA. Think about that. Angle P, angle A touch line segment PA. Then you've got another pair of base angles, angle T right up here, and angle R right here. Those are a pair of base angles because they touch the same base, and their base is TR. So 3 vocabulary terms that we ought to know that deal with every trapezoid out there. The bases are the parallel sides, the legs are the non-parallel sides, and the pairs of base angles, well, they touch the same base. All right, guys. So what we're talking about on this page, and I believe what I have for you on the next slide as well, these are universal things that apply to, and I guess I'm saying it again right here, all trapezoids. In just a moment on the next slide, in fact, I don't know if you can cheat and see over there on the left at slide number 3, we're going to talk about one specific type of trapezoid, but everything we just covered and everything we're covering right here on this slide applies to all trapezoids. And so, what do we have here, guys? I think this is actually a theorem in the book, but I don't have it numbered as such. I'll try to look that up and let you guys know. But here's an important idea. Pairs of non-base angles in a trapezoid are supplementary. Okay, pairs of non-base angles. So we had said a moment ago that angle P right over here and angle A, this one over here on the bottom right, that those were base angles. Therefore, a pair of non-base angles, and I realize now I probably should have said, oh, that was ugly, Mr. Fontana, don't do that. All right, my hand got in the way. All right, I probably should have said here consecutive. There we go. Okay, so we're talking here about angle P right there. Now, angle A is a base angle with angle P. So the adjacent angle that's not a base angle with P would be angle T. And those two angles right there are supplementary. That's what this statement right here says. The measure of angle T up on the top left plus the measure of angle P in the bottom left corner has to add up to 180 degrees. Now actually, now that I'm saying it out loud, that might not be a theorem in the book. That would explain why I didn't put it as a theorem. And I think it's because we already know this. If we go all the way back to chapter 3, we talked a lot about what happens when you have two lines which are parallel cut by a third line which is called a transversal. And when you do that, just focus on the yellow now, everybody, two parallel lines cut by a transversal creates 8 angles. These two angles that I have marked with tick marks, angle P and angle T, are what we call consecutive interior angles or same-side interior angles. And we learned a theorem way back in chapter 3, which we probably did in September, you guys, that already told us that when you have parallel lines cut by a transversal, that your consecutive interior angles are going to be supplementary. So, we already had a theorem that explains that. The exact same thing happens here, you guys. Line RA is a second transversal, and once again, angle R right here, I'll just put a dot there, and angle A right here, once again, form a second pair now of consecutive interior angles, and once again, those angles have to be supplementary. So the measure of angle R plus the measure of A is equal to 180. One thing I want to point out that I'm hoping makes sense to you, those two angles add up to 180. Those two angles add up to 180. And if you add up 180 and 180, the sum of the four interior angles in any trapezoid is 360 degrees. And I'm hoping that you guys remember from way back in section 6.1 that in any quadrilateral, whether it's a trapezoid, parallelogram, rectangle, rhombus, square, or a kite, which we're going to talk about here soon, in any of them, the sum of your interior angles is always 360 degrees. So that kind of meshes with what we think we knew already. So consecutive pairs of non-base angles in a trapezoid are supplementary. They add up to 180 degrees. Okay, guys, now what we're going to talk about next, this is not true for all trapezoids. This is only true for something special called an isosceles trapezoid. Now, we've certainly seen that word before, you guys. An isosceles triangle is one that has two congruent sides. So an isosceles triangle would look something like this, and that side on the left is congruent to that side on the right. Now, all we're doing here to make an isosceles trapezoid is we are cutting off this triangle here with a line that's parallel to the base of that isosceles triangle. And if I do that, and then if I just grab my eraser and get rid of everything that was on the top of that figure like this, and in fact I can get rid of that and get rid of that, oh, I've got this nice little symmetric shape right here, and this is what we call an isosceles trapezoid. Now, I do need to point something out. When we were all the way back on the first slide right here, and you guys for the first time saw the word trapezoid, you may very well have had an image in your head already of what a trapezoid looks like. And most people, when if they know it, when they think of a trapezoid, they think of one that looks like this, that is symmetric on the left and the right-hand side. You could kind of fold this thing right down the middle, and there would be your trapezoid. It's important to realize that a trapezoid doesn't need to have that symmetric property. This trapezoid that we drew right here and the one that I drew right here, these are examples of what I'd call generic trapezoids or a non-isosceles trapezoid. But now here we're specifically going to talk about an isosceles trapezoid, which is a trapezoid with congruent legs. So let's look at figure WXYZ, which is drawn for us right here. First of all, is it a trapezoid? Well, my definition of a trapezoid is a quadrilateral with exactly one pair of parallel sides. Pretty clearly, this figure is a quadrilateral, so check. And does it have one pair of parallel sides? Yeah, WX on top is parallel to ZY on bottom, but WZ on the left is not parallel to XY on the right. So yeah, this is a quadrilateral with one pair exactly of parallel sides, which makes it a trapezoid. And to be isosceles, it has to have congruent legs. Remember, everybody, your vocab. The bases are the two parallel sides. So we've got a base on the top and a base on the bottom. The legs are the non-parallel sides. So WZ is a leg, and XY is a leg, and sure enough, because of the red double tick marks there, we can see that WZ is congruent to XY, so this diagram is in fact an isosceles trapezoid. It's a trapezoid with congruent legs. Okay, everybody, that's the definition of an isosceles trapezoid, and that's an example of what it looks like. Let's learn a little bit more about it. Two theorems now, everybody. If a quadrilateral is an isosceles trapezoid, then each pair of base angles is going to be congruent. Let me see here. Do I have... I do. My smartboard, even the app I have on my iPad right here, it has a tool for making trapezoids, but you'll notice it only works for isosceles trapezoids. Okay, not really important, but anyway. All right, so let's draw ourselves an isosceles trapezoid that looks something like this. And now, this theorem is telling us that if we're dealing with an isosceles trapezoid, each pair of base angles is congruent. So if I were to call this figure J, K, L, M. There we go. All right. It looks pretty obvious here that JK is parallel to ML. Those are the two bases. Therefore, a pair of base angles would be angle M, and then let's think about this, the other angle that touches the same base as angle M. Well, ML is the base on the bottom. L is the other base angle with angle M. And this theorem tells us that those two base angles would have to be congruent to each other. That's not usually one I have to work real hard to convince people is true. This one kind of passes the eye test, everybody. You can look at that and go, oh, yeah, M and L look like they're pretty much the same. Again, because of the symmetry that an isosceles trapezoid possesses. You could just fold this thing over that dotted line right there, and yeah, it's going to match up perfectly. Now, that's not the only one, though. There's another pair of base angles. Those would be the two angles that touch the base on the top. So angle J right here is going to have to be congruent to angle K. So that's a nice thing that happens in an isosceles trapezoid that does not necessarily happen here. It looks pretty clear to me that angle P is not congruent to angle A. So it doesn't happen in what I'll call a normal trapezoid, but it will happen, in an isosceles trapezoid. And going along with the symmetry angle of this as well, let's talk about theorem 620. And theorem 620, let me draw another slightly different isosceles trapezoid, but there you go. Where did I leave off with M? So I'm going to call this thing N, O, P, and Q. Okay, and again, an isosceles trapezoid, and it looks like QN is parallel to PO, and QP is congruent to NO. Knowing that, guys, what's going on here? This theorem tells us, again, something that I think passes the eye test. If this quadrilateral is an isosceles trapezoid, then its diagonals are congruent. The diagonals, everybody, are a line segment that connect two non-consecutive vertices. So if I were to start at point Q, the two vertices to which Q is already connected are N and P. The one it's not connected to is O. So line segment QO, everybody, is one of our diagonals. Okay, so I'll draw that going across. The other diagonal would connect the only 2 points here that are not already connected, which would be P and N. And when I go to connect P with N, I'm just going to ask you guys to look at that one right there, but I think you can see it. Those two segments right there are exactly the same length. So we would say that diagonal QO is congruent to diagonal PN. That, again, is because of this symmetry property of an isosceles trapezoid. It doesn't happen here. In this figure, I'm going to erase this as soon as I draw it, guys. I've got a diagonal that's not what I wanted. Actually, that worked fine. A diagonal that goes from P to R, and then another diagonal that goes from T to A. It looks pretty clear to me, everybody, that line segment TA is longer than line segment PR. So they're not going to be congruent in every trapezoid. They are only going to be congruent in an, there we go, isosceles trapezoid. All right. So that is that. All right, guys, and we are moving right along right here. Okay, what's going on next? Here's a phrase that shows up that we don't hear very often, the midsegment of a trapezoid. All right, and the midsegment of a trapezoid, let me try to follow my own organization right here, guys. In part A, I was talking about all trapezoids. Then I shifted gears to part B of these notes, which were just isosceles. And now for part C, we're going back. Okay, so this again really is true for all trapezoids right here. Okay, midsegment of a trapezoid. Here we go. It's the segment joining the midpoint of the two legs. So, because this is not unique to isosceles trapezoids, I'm going to draw kind of a weird one here, guys, that's going to look maybe something like, let me draw a figure like this, and then just to really mess with you guys, I'm going to draw something that looks like that. That is an ugly four-sided figure, but what I'd intended here was that the bottom was going to be parallel to the top. So those are your bases, and the other two sides are not parallel, so there we go. A midsegment, everybody, joins the midpoints of your legs. Now the legs are the non-parallel sides. So let me call this figure, I just looked at the word legs, so L-E-G-S. L-E and S-G are parallel, those are the bases. So the legs are L-S and G-E. Now I'm just going to guess right here, but I'm going to say that point Y is going to be the midpoint of L-S. I'll need tick marks to show that. And I'm going to say that right over here, point Z is going to be the midpoint of GE. So I'm going to do a double tick mark there and a double tick mark here. And now the mid-segment of a trapezoid is the segment that joins the midpoints of the legs. So if I draw the line segment that goes from Y to Z, this one right here is called the mid-segment. I'll abbreviate that, guys. That's the mid-segment of a trapezoid. And Theorem 621 tells us two interesting facts, everybody, about a mid-segment. First of all, and again, I think this one passes the eye test too, the mid-segment is parallel to the two bases. We already knew that LE up on the top and SG down on the bottom were parallel. This YZ in the middle, is parallel to those two as well. So that's the first little conclusion of that theorem. The second one, this one kind of makes some sense. The length of the midsegment is half the sum of the lengths of the bases. And this phrase right here, half the sum, everybody, if you take two numbers, add them together to get their sum, and then take half of that, or divide by 2, you are finding the average of those two numbers right there. Okay, you are finding the average of those two bases. So let me give you a really simple numerical example here, guys. If we were to say, let's make this really easy, that the measure of SG was 10 units long. LE up on the top definitely looks longer than that. In fact, it looks about twice as long as that, roughly. So I'm going to go with a 20 right up here. This little theorem here, Theorem 2, says that the length of the midsegment, YZ, is half the sum of the length of the bases. So the measure of YZ would be 1/2 the sum of 10 plus 20, which would be 1/2 of, well, 10 plus 20 is 30, and last I checked, half of 30 is 15. 15 is the average of 10 and 20. I don't think it's going to surprise everybody that the length of that piece is bigger than 10, kind of looks that way, and less than 20. But what might be surprising to you, I don't know, it's exactly halfway in between the 10 and the 20. All right, so let's look at this example right over here, everybody. There's a reason this is here, and I'll show you that a little bit later. All right, so what's going on in this problem? All right, I see a quadrilateral in blue. So I know that for sure. And I see two red arrows here, everybody. I see that the top segment is parallel to the bottom segment. So that means that we're dealing with a trapezoid. If we look at the tick marks on the left and the right, let me call this point A over here and this point B. The tick marks tell me that A is the midpoint of one of the non-parallel sides, so it's the midpoint of a leg. B, because of the double tick marks here, is also the midpoint of a leg. So that means, everybody, I'm not making any assumptions here, that the red segment in the middle of the figure here is the mid-segment of this trapezoid. It connects the midpoints of the two legs. And we're talking about the lengths here of one of your bases, a second base, and your midsegment. So I've got to go back to that theorem that we just wrote down that said that the length of your midsegment is 1/2 of the sum of the lengths of your bases. In fact, I'm going to write that down in words. You guys won't normally do this, I don't think, but the length of your midsegment means equals 1/2 the sum of the two bases. That's really ugly. All right, let's fill in what we know. How long is our midsegment? That's this piece right here, 2x plus 4.5. And that equals 1/2. When you see the word of, everybody, that always means multiply, and with a sum, I'm going to need parentheses. One of my bases is 5x minus 4, and I'll add that to my other base, which is 3x minus 7. That's our equation setup, guys. The length of the midsegment is 1/2 of the sum of your bases. And let's fill in what we know, guys, or I should say let's simplify here. 2x plus 4.5 is equal to a 1/2. And now in parentheses, the 5x plus 3x is 8x. And a -4 minus 7 is a -11. Now, right here, people disagree a little bit on what we ought to do. It is entirely possible to distribute the 1/2 over here in order to do that. The reason I don't love it is that 11 is odd, and that's going to get me a decimal number. But you know what? I got a decimal over here on the side, so I guess we'll just deal with that. So we've got a 2x plus a 4.5 is equal to half of 8x is 4x, and half of 11 is 5.5. So now, guys, we have a really two-part equation right here. We've got x terms on both sides and constants on both sides. So don't embarrass me when you guys get to Algebra 2 next year. We got to know what we're doing. We move the x's first. We move the smaller to the larger one. So I'm going to subtract a 2x from both sides, and that'll move all the x's to the right. Therefore, all the constants need to get moved to the left. So I move a negative 5.5 by adding 5.5 on the right and doing the same thing on the left. Those two x's on the left cancel. Those 5.5s on the right cancel. And I'm out of room, so I'm going to move back up here to the top right now. 4.5 plus 5.5 is 10. 4x minus 2x is 2x. And now we'll divide, that was right. Divide both sides by 2, and we'll end up with x equals 5. Now, I certainly think that answer is right. Let's check it, everybody. Up on the top, 5x minus 4. 5 times 5 is 25, minus 4 is 21. There we go. Down on the bottom, 3 times 5 is 15. 15 minus 7 is 8. In the middle, 2x, that's 2 times 5, that's 10. 10 plus 4.5 is 14.5. Okay, so with that in mind, everybody, I got a calculator around here somewhere. Hang on just a minute. Where? Here? There? Should be over here. You'd think Mr. Fontana would know where this would be. All right, we'll just go with a regular scientific calculator. Nothing. Oh, I got to download that? All right, I'll go with this fancy calculator, which is way more than I need. Anyway, but let's run with this. When you're super cool like Mr. Fontana, you have 5 different calculator apps on your iPad or your phone. Anyway, back to it, guys. What we thought we knew there was that the two bases were 8 and 21. I want to make sure that that 14.5 is the average of those two numbers. So what I'm going to do is do a fraction, everybody. And on the top, I'm going to add 21 plus 8. And then down on the bottom, we're going to divide that sum by 2. Okay, Mr. Smart Aleck, I wanted the decimal version of that, which is going to be, there we go, 14.5. Okay, and that is the average of those two, and that's the length of our mid-segment. All right, so I feel pretty good about that. The last thing we're going to talk about, and I'm really not going to do much with this, guys, although there are some questions on the homework here, we're going to talk about kites, which are a weird one, everybody, and let's talk about why. A kite is defined as a quadrilateral, so let me stop right there, not a parallelogram, not a trapezoid. So a kite, in all likelihood, isn't going to have any pairs of parallel sides. So a kite is a quadrilateral with 2 pairs of consecutive sides congruent. Now, that can be a little bit tricky because, let me add a page right here. We learned a while ago that if you have a quadrilateral in which both pairs of opposite sides were congruent, if the left is congruent to the right and the top is congruent to the bottom, then this figure right here is automatically a parallelogram. This is what it looks like when you have 2 pairs of opposite sides parallel. Congruent. The top is congruent to the bottom and the left is congruent to the right. Those are opposite sides. But in a kite, everybody, we're talking about consecutive sides being congruent. Line segment KI right here and line segment KE are right next to each other. They share a common vertex here at point K, everybody. So those are what we would call consecutive sides. They're right next to each other, and you'll notice they're congruent. Likewise, let me shift colors on you here, line segment TE and line segment TI. Those are consecutive sides as well. They share a vertex at point T, and if we look at the double tick marks here and here, those consecutive sides are congruent as well. So that is what a kite looks like, everybody. And if you were to ask a little kid, maybe a second grader, what does a kite look like? This is the shape they would normally draw. So it's one of those things you probably knew even before you formally defined it. Okay, so that's what we're saying about a kite, everybody. It's a quadrilateral with two pairs of consecutive sides congruent and opposite sides not congruent. All right, Ki in this figure is not congruent to ET. Ke is not congruent to IT. So that is the definition of a kite, everybody. But we've got 4 properties that we need to talk about here that go along with it. First of all, in a kite, one pair of your opposite angles are congruent. And in this figure, it's going to be angle E all the way over on the left is going to be congruent to angle I. And I'm talking the big outer angles here, E and I are congruent. K up on the top and T down on the bottom are not congruent. Next one, and this one's actually a theorem in your book, 622, the diagonals of a kite are perpendicular. Line segment KT is perpendicular to line segment EI. Okay, this is where it gets weird now. The third property, one of the diagonals bisects the other. So if these two diagonals intersect at a point in the middle that I'm going to call S, S is the midpoint of one of the diagonals, but not the other. S is the midpoint of EI, everybody. So we're going to go ahead and say that line segment ES is congruent to line segment IS. But it is not the case that KS is congruent to TS. I think you can see that. And then number 4, let me slide that up a little bit. One diagonal bisects the original angles of the kite. Now that is what happens up at the top at angle K. So I'm going to say angle K, and down at the bottom here, and angle T are bisected. They're cut into 2 congruent parts here by line segment KT. But that did not happen over here on the left and over there on the right. Okay, so those are, we've got the one definition and the 4 properties now that go along with kites. So if you guys have these notes in front of you here while you're doing your homework on kites, I think we're going to do okay on that. All right, everybody, that is a wrap for what I have for you here in section 6.6. So let's give that homework a try and let me know if you guys have any questions. Good luck, everybody.